Is there a pointer? Yeah, thank you. So, good morning, everyone, or good afternoon, good evening. For some people, even good night. Woke up especially to attend this conference directly from the start. So, good morning, everyone here. And I'm very pleased. I would like to introduce this talk on battery deionization for electrochemical water polishing. And this talk has been prepared as a joint effort together with Bert van der Wal and Slavomir Pohada. Slavomir is assistant professor now in Wroclaw University, Poland, and we prepared this talk together. So there's work of all of us. So since 2014, what happened ever since, and what have we been working on, and what to expect in the coming years? These are topics that I would like to discuss with you today. This is a great picture taken in Leeuwarden at a conference. Then it was indeed a special session on capacitive deionization, about 80 people, I think. So what have we been working on? Well, here you see a system, CDI system developed by Voltia. You have seen many times already. And well, several applications we had in mind for CDI technology. And one of these was desalination for example, cooling towers. So we had a research interest in many different topics, in new materials, in theory, to understand the performance of the system, to understand the energy consumption and how to optimize this. Work has been done on developing metrics to compare systems, on studies on long-term performance, very important, understanding and analyzing the energy consumption and how to reduce this by reducing resistances, studies to increase water recovery, and very important also studies to understand the pH effects. And this is related to long-term stability. And I want to start with that, the topic of pH effects. I discuss it briefly. So what did we do? We studied pH fluctuations of CDI systems, MCDI systems in the lab at different conditions. And one of these conditions is the desalination of water streams with sodium chloride, only sodium chloride present, low concentrations. We studied these first theoretically, a paper published in 2017. And after that also Anthony Hourajan, PhD student, did experimental work on this. And very interestingly is that we saw during the adsorption, we observed an increase of the pH. We observed this theoretically and experimentally. And during the desorption, a decrease. Well, if this would be the pH profile that also applies to real water systems, CDI is, well, I think that's what Bert van der Wal mentioned yesterday, MCDI would have been easily upscalable and technology that would be a big success directly from the start because you wouldn't need any chemicals to regenerate it. But there are some challenges. And that is because when you start to desalinate tap water, you observe a decrease of the pH during the adsorption step and an increase during the regeneration step. And this increase is a problem because if your pH increases and you have high salt concentration, especially of calcium ions in your space, you observe scaling, and that is something you do not want. So we wanted to understand this better, and Anthony did experiments also with synthetic water solutions to observe whether we had pH changes there, and with sodium bicarbonate solutions. And in all these cases, we observed a pH increase during regeneration. And we mainly relate this to the presence of bicarbonate ions in solution. And that is a challenge. That's something that we want to understand better. Anthony also performed experiments at different water recovery values. And we observed that with increasing water recovery, what we all want, we have higher pH values. And so what we observe is that the pH increases in magnitude with the water recovery, and pH changes become smaller in a double anion exchange membrane configuration in MCDI. And that's a very interesting topic to learn more about, but that will be covered tomorrow by Min-Shen Wu, who did this study together with Anthony Ahuja-John, and Min-Shen will elaborate on these experiments in her talk tomorrow. Well, we've been doing other work as well, because the first interest is to study and understand these pH fluctuations and also to reverse these pH profiles, these pH changes. But another interesting topic is to understand and work on the potential of CDI technology for very specific applications. Because if you can use it for a specific application, other technologies may not be able to work well for you may use and develop this technology for that. So there are several topics I want to discuss in this presentation. And the first is electrochemical water polishing for the removal of boron, arsenic, and other components. After that, I want to discuss the topic of selective separations. And the work of electrochemical water polishing that has been done in a joint effort with the group of Matthew Suss and Amit Chokhan, who is here at this conference, and here guys, Maarten Biesheuvel. So joint work, published first paper in PNAS in 2020 and 2021, and second paper in Chemical Engineering Journal, published very recently this year. So why is this interesting, and what can we do with this concept of polishing a water stream to remove certain species like boron? And I will focus now on boron. Well, what is the challenge, or what is the problem if it comes to boron removal and also with arsenic removal, is that with conventional desalination technologies like reverse osmosis, boron can pass the membranes easily. And why is that? Well, under natural water conditions, on the normal, regular water conditions at a regular pH values below 9, boron is mainly present in an uncharged form. And this uncharged form that is predominantly present, for these ions, the removal with reverse osmosis is not effective. And why is that? Well, in charged form, these boron acid species, they are rejected, boric acid species are rejected by the membrane, partly because of charge repulsion, but also because they carry a water shell, and therefore they are somewhat larger. Under neutral pH conditions, they are smaller because they do not carry a water shell with these, and they are not charged, and they can, well, pass the membranes easily. And for that, because of that, the rejection of boric acid by reverse osmosis membranes is quite limited and is often, well, below 60%. So we are thinking of a concept to use reverse osmosis first for seawater desalination. First a step with reverse osmosis to remove the salt. And then we have a solution with a certain amount of boric acid. And this solution we want to polish to remove boric acid. And that's what we do in this cell, where we have 2 different electrodes, which we charge to absorb boric acid, and with the aim to produce a solution, a safe drinking water solution without boric acid. Well, how did we work on this? How did we develop this? Well, we built a model in that contains several elements. In this model, we consider ion transport in the micropores, and we also consider acid-base equilibria in these micropores between the different boric acid species. And we consider the micropores in which we have electrosorption, in which we also consider chemical equilibria with the surface groups. And then we consider 2 different types of group, acidic groups and basic groups. We have transport in the micropores, and for that we evaluate transport equations, and we set up one general equation per group of species or per family of species. So, and this allows us to get rid of reaction terms in these equations. I will not go in detail here, but we will set up one equation for a group of boric acid species. And we evaluated transport of boric acid species considering advection, diffusion, and electromigration. Furthermore, we evaluate, so here we evaluate one equation for the group of boric acid species. So that is resulting equation that we evaluate, and we evaluated charge balance. Lastly, we consider chemical equilibria equations. In the micropores, acidic micropores, we consider that the chemical surface charge density is a function of the proton concentration, and we do the same in the basic groups where we have groups that also can take up a proton, and we evaluate then the ion concentrations in the micropores. So these ion concentrations in the micropores, they are a function of the charge, of the potential, Donon potential, but also function of the local pH. And then we did simulations, and we did simulations. We first didn't know how to set up the salvator, so we did simulations with different electrode orders. At first with a cathode placed upstream, and we did not observe any removal at all of boric acid. And we were actually surprised. We thought that if you would place the cathode upstream, you would be able to take up the protons in the cathode, absorb the protons there, and by that get boric acid in the dissociated form. Well, we didn't observe any removal of boric acid. When we placed the anode upstream, we observed a removal of boric acid, and we were actually quite surprised. And to elaborate a bit on this, I want to explain the pH profiles that we observed over the cell. What we found is that when you place the cathode upstream, you get in this cathode not a high pH, but a very low pH, and this low pH propagates in the anode. Well, there's where you want to absorb the boron acid, the boric acid in charged form. And well, that is not possible because for that you would need a high pH. So low boron uncharged conditions, no removal of boric acid. When we place the anode upstream, we observed a high pH, higher pH in the cathode, low pH at first in the anode, but then there is this front just in the anode where you have a high pH very locally, and you can use this to dissociate uncharged boric acid, get it in its charged form, and then absorb it here. So therefore, we have specific locations in the upstream electrode where we are able to absorb boron acid. Well, a model is nice, but it's also very useful if you can validate it experimentally. So a lot of experiments have been done in the group of Matthew Sass with these different configurations, and we also observed experimentally that when you place the anode upstream, that you are able to remove boric acid effectively. So why do we observe this pH increase in the upstream electrode? Well, what we think, and it's of course very hard to really, well, describe it or to really state what the cause is, but what we want to have in the upstream electrode, which the solution enters a limited absorption of hydroxide ions, and in the cathode we want to have a strong proton absorption. And to increase this pH, the protons must be electrosorbed. That's important. Well, these protons, they are electrosorbed in the cathode. For that, you need a low sodium concentration, because otherwise the sodium ions are electrosorbed. Well, and that's what you have when you place the cathode downstream, because then you don't have competition with sodium ions. And this will result the absorption of protons there in the production of hydroxide ions, and these will propagate upstream due to an electric field. And then due to that, you develop so these will propagate upstream, these hydroxide ions. For that, it is important that the flow rate is not too high, because otherwise convection will take the hydroxide ions to the exit. Then you get a pH increase there and you get boron removal. Well, very interesting. We thought the higher the pH, the better the performance. And then lately, Amit Chakon did many calculations, different cell voltages, different discharge voltages, and decrease the discharge voltage. And interestingly, what we observed is that when you decrease the discharge voltage, your boron absorption will go up, while your pH at this separator anode interface will go down a bit. So it is not only the mechanism that I just explained of the high pH, the higher the pH, the higher the boric absorption. That is not completely true. There's something else going on as well. And in these nice plots, you observe at the different discharge voltages, the ratio of the charged boric acid over the feed concentration with position time. And when you have a lower discharge voltage, we observe that we got more boric acid in the charged form. Well, interestingly, with these theoretical calculations, you can also calculate the contribution of the different transport mechanisms to the transport and of boric acid. And what we observed is that at certain pH conditions, at this lower discharge voltage, that we have a strong migration, a strong negative migration of negatively charged boron to this interface where we have a high pH, where we can absorb boric acid in the anode, the upstream anode. So boron absorption is higher at lower voltages, and this is other than what we expected just based on pH. So it's very interesting. We have a complicated interplay of all different mechanisms, and in order to understand it, to give some, well, to be able to understand it, it's very helpful to do these calculations, but even then it takes a long time to, well, understand what you observe. Well, can we use this technology? Can we develop it to reach the required levels of boric acid in the effluent? So the WHO and the European Union set guidelines for the maximum concentration of boric acid. And here you see the boric acid, well, the theoretical concentration of boric acid in the effluent as function of the discharge voltage, and also experimental data. Now, there are several things to conclude. One thing is that we can continue improving our theoretical understanding, because there is some difference. There is some difference between the theory and the data here at very low discharge voltages. So what exactly goes on, that's something we still want to understand. But what we also observe is that under certain conditions, we are theoretically able to reach the effluent concentrations, maximum effluent or maximum concentrations of boric acid that are allowed in produced drinking water. If we reduce mixing volumes, we are able to get, as function of time, this is a graph as function of time, short intervals in which we have an effluent boric acid concentration that is below the maximum values that are set. And if we play with the starting time of the moment that we start to collect the boric acid solution or the desalinated solution, we are able to reach values below the required values that are, well, maximum values that are set as well. So I think there's an interesting, well, it is interesting to develop CDI as a technology for post-treatment after certain technologies to remove, for example, uncharged species like boric acid or arsenic or some organic micropollutants. And it's very nice to see that others have been working on this challenge of boric acid removal as well. And this group of Kyung-Hong Shin worked on electrically assisted reverse osmosis, where they coated a porous electrode on a reverse osmosis membrane, also with the aim to remove boric acid. And they observed that when they applied a certain voltage, that they can increase boron rejection by this reverse osmosis system, that they are able to avoid the presence of boric acid in the produced water solution. Other studies include the use of a bipolar membrane to produce hydroxide ions to increase your pH and therefore get boric acid in dissociated form, studied by the group of Elimelech. And a study by the group of Wade is to use an anion exchange membrane, a combination of an anion exchange membrane and a porous carbon electrode, also with the aim to increase the pH, to get boron in a dissociated form, and to electrosorb it. Very interesting work. And if we look at the results that we have so far, I think we are developing a promising concept. All these technologies, or not all of them, but some are able to reach sufficiently low boron concentrations. We are able to achieve quite high productivities, I would say, the order of 10 liters per square meter membrane area per hour. But I also have to say that there is a big challenge, and that is that the water recovery is rather low still. And no one wants to apply a post-treatment technology after reverse osmosis and have a water recovery in this post-treatment technology in the order of 20 to 30%. That is something we want to avoid. So we have to increase the water recovery and we have to continue working on this. So it is, I think, an innovative concept for electrochemical water polishing to remove certain species, but improvements in terms of theory and also in terms of technology are still required. It is interesting that this is an application where you have this cell downstream where no calcium ions are present in the feed, and you will not, due to that, you will not have scaling. Another promising topic is ion selectivity in capacitive deionization. Well, many people have been working on it, and at Wets's Tanya Mibita did work on this, or nitrate chloride selectivity. As you see, well, there are many studies in this field, and it's very interesting to determine under which conditions you have maximum selectivity and how you have to operate a cell then. And it's also interesting to determine whether selectivity is due to the porous carbon electrodes or due to the membranes if you apply MCDI, and whether you can achieve selectivities in electrodialysis and a CDI, so to compare different technologies for selectivity. And this is also what Tanya did. So she did this first with CDI, capacitive deionization, but then she also did experiments with electrodialysis. And also in electrodialysis, you are able to achieve high selectivities, but only at the start. And then when you develop a concentration gradient between the concentrate and the dilute stream due to time that is passing on, so you are desalinating, it's in batch mode, so you continue the desalination or the separation process, you develop a concentration gradient between concentrate and dilute, and due to that, your selectivity decreases. So this is a problem in electrodialysis. But we are wondering, and that's something, and these systems, membrane-based systems, electrodialysis and MCDI, and electrosorption-based systems, CDI systems, the group of Matthew Sess did a very big effort, very interesting effort to compare all the selectivities that have been reported for the different ionic species in literature. And you see that, well, with membrane-based systems, you are able to achieve selectivities significantly high, and with CDI as well for the different ionic species. One thing I find this plot is really nice. Well, and then many people know that I would come with a but I like this plot a lot. There's only one thing, and that's the combination of MCDI and ED in one plot, because I think there is a significant difference between these two processes. And that is what I want to illustrate here. So what we observe in electrodialysis is that with an increasing concentration gradient between your concentrate and dilute, your selectivity decreases. But what if we would be able to place porous electrodes in your concentrate channels, and by placing these porous carbon electrodes, we are able to absorb the species that were preferentially transported? Can we then keep up our selectivity for a longer period of time? I think that's, well, interesting to maintain selectivity in electrodialysis by the aid of porous carbon electrodes. Well, inserting porous carbon electrodes in electrodialysis is, I think, the same as inserting membranes in capacitive deionization. You obtain processes that are quite similar. And Choi Lee, PhD student at Wageningen, did calculations on the comparison of different materials and the selectivities introduced by the different elements in this cell. So see a compared non-selective electrodes, and then introduced a selectivity, a mu affinity term for calcium, a selectivity of the membrane towards calcium, and in a system with non-selective electrodes. And she compared this with calculations in a system with selective electrodes, and then also adding a selectivity to the membrane towards calcium. And what we observe is that in these cases, the selectivity of calcium, the absorption of calcium is more or less the same, but selectivity or the absorption of sodium decreases with an increasing mu affinity towards calcium. And if you compare the non-selective electrodes with the selective electrodes, you observe that you are able to absorb more calcium than sodium in a system with selective electrodes. We have to explore this. This is theoretical. We want to explore this experimentally. And we also want to understand this way better. So these are first calculation results, but I think there's a promise to apply the combination of selective membranes and selective electrodes to have a more selective process. So these are calculations done by Choi Lee, PhD student in Wageningen. Well, there are other interesting topics that we can explore. Many of you know that there is an increasing interest in the removal of PFAS, perfluorinated components. These are persistent, and there is strong legislation that tells us that we have to remove PFAS from drinking water. So the new proposal sets the maximum required concentration of PFAS at 4.4 nanogram per liter. And it's challenging to remove it. There are different processes that one can apply. One is absorption, but there are also big challenges. And what we know with absorption is that when you absorb it in activated carbon columns, you are able to absorb PFAS from water, but you have to, after 30,000 bed volumes, after a certain operational time, you have to regenerate the materials. And that's something that requires a lot of effort, because you have these big carbon filters and they have a relatively fast breakthrough, so you have to regenerate them frequently, and you have to transport these filters, and they are regenerated at high temperatures in special facilities. So if you're able to develop an in situ regeneration process, perhaps with the concept of electroabsorption, I think that would be very interesting. But it's also very challenging because you have many competing ions. So applying electroabsorption during the charging step can be quite challenging. Well, I'm very happy to see when I'm reading literature that this topic also gained interest by the group of Xiaoxu. And this is recent work, so it wouldn't surprise me if you will elaborate during the conference on this. So I will not say much of what I read. That's all up to Xiaoxu, but I think it's interesting field to explore. But there are also many challenges, how to keep up system for a long period of time and how to achieve selectivities also in real water streams towards these perfluorinated components. So important topics for CDI, chemical-free desalination, of course, to avoid scaling. It would allow you to apply CDI at specific sites where the transport of chemicals is hard, as mentioned by David Wade. I think electrochemical polishing as a post-treatment step after membrane treatment is interesting for the removal of boron, arsenic, other pollutants, ammonium, and to improve our theoretical understanding and technology development are still required for that, to develop it as an electrochemical water polishing step. Furthermore, I think it's interesting to work on ion selectivity, especially also in a combination with membranes and porous carbon electrodes, and to develop systems for the removal of non-biodegradable pollutants that are present at very low concentrations. And with that, I, but also Slavomir and Bert, would like to thank you for your attention.
Today is finished this
conference? No, conference is tomorrow and
well, thank you very much, Jouke, for well, I can say a very nice presentation, nice overview also of the literature that has been done on in this field. I'm sure there will be some questions, and I would first like to start with the live audience, and then I will also see if there are some questions online, which I actually cannot see. So the organization needs to help me with that. Is there any question for Jouke?
Thanks, Jouke, for the great talk. I was actually just sort of curious because I think in one of the technologies you have these sort of pH changes that affect the boron. How much does the pH change at the interface of the electrode versus the bulk? Do you sort of, does the pH drop a certain number of units because?
Yes, so I think in the plot that I showed, we had a local pH as function of position, and the inlet pH, the inflow pH was around 7. And then at this peak where we were actually absorbing boric acid, we had a pH in the order just above 8.5, 8.59 in that order. So we were able to increase this pH from, well, let's say 7 more or less in the influent to value of 8.59 at this specific location where we could absorb boric acid.
And that's purely due to the proton accumulation?
That's purely due to, I would say, the water chemistry, the dissociation of water into protons, hydroxide ions, and then the protons being electrosorbed in the downstream electrode. So there's no Faraday reactions included. It's all electrosorption and transport.
Thank you.
Well, thank you for the question. Is there any further question from the audience here?
Great presentation. Thank you very much. I'm very intrigued by using this approach for PFAS removal. There's a lot of people that are doing research just on active carbon absorption of PFAS. How much did CDI improve over just active carbon absorption itself?
Yeah, that is a very relevant and very important question to explore, I think, in the coming years, whether with electrosorption we can improve the absorption. And also, I think in particular, whether with electrosorption we are able to regenerate a system on site. And right now, yeah, I think that is a topic to work on in the coming years. I would not know, but perhaps Xiao Sun knows much more about this, and he will present. You will present Tuesday, Wednesday. Yes.
Awesome.
So,
thank you.
Looking forward.
We hold on to this question, and then we will get the answer this afternoon. Yeah. David.
Just on the pH issue, you attributed that to gain and loss of protons and hydroxide ions for the most part. What about bicarbonate removal in charging and then increase in discharging? Surely that'll be important as well.
Yes, I think indeed changing to real like solutions in which we have significant bicarbonate ions, I think that will change what we observe, and that is a very important development to explore in the coming years, and that will definitely affect the removal.
any open system will have some bicarbonate because of CO2 influx.
Yeah. Yeah.
One more question over there. Are there also questions online or not? Can you see that? No questions online. Okay.
If you shout out, I can repeat your question.
Hello, can you hear me now?
Yeah.
Hi,
Excellent.
really nice talk. So my question is based on the local pH gradient. So it looked like a very small part of the electrode actually had this pH spike in which the boric acid can be concentrated. So can this pH gradient be induced at a earlier like gradient? Can more of the electrode be used for inducing this pH gradient, and will that improve the boron removal capacity of the electrode?
Well, that is a relevant question. Perhaps then we can keep up the period of time in which we are removing boric acid. That we are able to keep up this period of time we can keep up this period for a longer period of time. That would be very relevant. I think right now we always are the zone, and there's a reason for that. That's because the hydroxyl ions, they come from your downstream electrode. They have to migrate to the upstream electrode. But if there are ways, if you think of ways to use more space effectively, that is would be interesting.
Thank you.
Okay, then also in the interest of time, I would like to thank you one more time, Jouke. And then we move on to the next speaker. And I had to practice a little bit on the name because this Professor Shin Choi.
Excellent.
I see I passed the exam. That's always nice. She was born in Korea, also got her master's degree here at Seoul National University. Then she moved to the US, and I think you got your PhD from Michigan State University. You're now a professor in chemistry at University of Wisconsin. And one of your areas, I looked it up, but you have a very broad interest in different types of areas. But one of the areas is electrochemical desalination. And that's what you will talk about here today. So the floor is yours.
Okay. Hey, good morning, everyone. It's a pleasure to have the opportunity to tell you about what we do. I would like to point out two things. Last night, I was informed that I am the only chemist in this conference. Is that true?
Yeah.
Okay, so you will get to hear what kind of a water desalination research can be done by a chemist. And second of all, I'd like to point out that I am from Wisconsin. If you are not familiar with the map of USA, the nearest largest city is Chicago, and we are 3 hours north from Chicago. I counted how many hours I had to fly to get here. 16 hours just on the plane, and I had 2 connections. That's 6 hours, and then driving time to the airport, in total 24 hours. So just please know that the time that I took to get here is directly proportional to my enthusiasm to attend this meeting. And I'd like to see if there's anybody else who traveled longer. Thank you. Thank you. Okay, so today I'm going to tell you what kind of a water treatment research can be done by bismuth-based electrode. And then I think with this audience, with this audience, I don't think I need to explain the need to, for desalination, but since I have this slide anyway, I'm going to say a few things, okay? So this map is color-coded. So if you, look at your hometown, and if you're living in a green region, you are just fine. If you live in a yellow region, that means 1 month out of the year, your need for fresh water is more than the supply, right? So if you live in this dark brown region, that means 12 months out of the year, basically, you are thirsty. You need to do something. And then as you know that our earth is covered with a 90, 7% seawater, and fresh water is only 25%. And even for this, 2.5%, a lot of them we cannot even get access to it. So the obvious solution for desalination would be the seawater desalination. And then when I first got into this field, which is 2015, I was studying. I wanted to, as an electrochemist, I wanted to do something for desalination because I, consider that this is a serious issue. And in order to come up with a new idea, I wanted to learn about then currently what is the best method for seawater desalination. And obviously reverse osmosis is the answer for the seawater desalination. And if you see this, basically it's a membrane-based technology, and then we use a semi-permeable membrane, and through these pores, water can go through, but salt cannot. And then by osmotic pressure, typically water molecule has to move to the salty area, but we are going to apply the pressure to compensate for the osmotic pressure, and we are going to add even more to squeeze water molecules through these pores, and that's how you end up doing desalination. But as some of the previous speakers already mentioned, here you have to apply a high pressure, and then the pressure you need to apply is strictly proportional to the salinity of the water that you are dealing with. So at least for the desalination RO, you don't need to apply that high, although it's still very high. For the seawater desalination, you have to apply 55 to 82 bars for seawater desalination, and you can imagine the power you need and the noise and everything, the entire plant, you have to use a special nut and bolt to tolerate this pressure, right? And then even before you start this process, because the membrane is the key, we have to do the pre-treatment, right? You have to try everything to remove bacteria and then control the pH to minimize the scaling, right? So even for this pre-treatment process, typically they don't even think about the cost for this part. They just think about the electricity, but there's a post pre-treatment process. And after that also, as you just heard, there had to be a post-treatment, right? So if you add all of them, it's going to be quite costly, okay? And then also here, after you do the desalination, the leftover part, brine, what are you going to do? You need to do something, right? So then if you just flow it back to the seawater, basically you're going to kill a lot of aquatic species, right? And then typically what I learned is they're going to make a pipe underneath, and then they do the deep sea injection, but it's just going back, it's going back, right? And then if you do this RO in inland, after you create this brine, you have to transport to somewhere else, right? So that brine management cost, people typically don't think about it, but that can easily become a deal breaker for doing a reverse osmosis in inland desalination. So that's that. And the electrolysis, again, I think all of you are very familiar with this. Again, this is membrane-based technology, and then ions are moving through ion selective membranes. But again, at the same time, whenever you do desalination, you generate brine, and then this is not ion selective. So based on this, we wanted to think about, can we come up with a new desalination method? And what we wanted to focus on is, can we do something to make a device that can do desalination without membrane? And then can we do ion-specific removal? And then can we do better brine management? After we remove Na and Cl, what can we do when we recover it? Can we use it for something useful? And then in addition to desalination, chloride removal in wastewater can be a serious issue. If you know the, like industry in USA, Wisconsin is our, dairy state, meaning I think all the cheese that are generated in USA is generated in Wisconsin. And then in order to generate cheese, we have to use a lot of salt. So there's a chloride level very high in wastewater. And then also Wisconsin is extremely, extremely cold. Our winter is typically 5 to 6 months long. And then, lots of snow. And in order to do the road de-icing, we have to put a lot of road salt. So they also go through the wastewater. So the chloride level is higher than the regulation from our EPA. The problem is in wastewater treatment, they have no cost-effective way to remove chloride. So if we can come up with a way to specifically remove chloride, we can help the state. And it's just not Wisconsin. A lot of Midwest states, they are suffering from the use of hard water. So they use water softener, and then the chloride level is a problem for many, many states in USA. Okay. So with this idea, the device that we started to develop in 2015 is called the desalination battery. And then our desalination battery is specifically using bismuth-based electrode, and that's the focus of my talk today. So this is a nice scheme here. If you inject water, if we can have a sodium storage electrode and chloride storage electrode, you can remove sodium and chloride ions, and it's going to spit out fresh water. And what if this process is thermodynamically downhill? So then the electricity is going to come out and you can actually use it to lit up the bulb. So can this be possible? So just to start with how this desalination battery works, I'm going to show one slide about how the typical batteries work. For lithium-ion batteries, basically what you need is a 2 lithium storage electrode, but you are going to choose 2 electrodes such that their radiation potentials are different. So lithium moving from this storage electrode to that storage electrode is thermodynamically downhill. So then the electricity is going to come out. I think this is a very interdisciplinary field. So even the simple terminology, discharging, charging can have a different meaning. For my talk, whenever I say discharging, that's a thermodynamically downhill process. So the electricity comes out, like typical battery operation. So after lithium is all moved from here to there, then you are going to send these lithium ions back to the first electrode. Then that is exactly the reverse reaction of the forward reaction. So if this is thermodynamically downhill, this has to be thermodynamically uphill. So this is the charging process of your battery. In battery community, a lot of researchers are also interested in developing sodium-ion batteries because sodium ions are cheaper than lithium ions. So then if you want to make sodium-ion batteries, what do? Simply, you use the same principles, but this time you're going to use sodium storage electrodes, 2 of them with the 2 different sodiation potential, and this is what you do. So after we understand this, we are wondering, what if instead of combining 2 sodium storage electrode, what if we find chloride storage electrode and combine it with a sodium storage electrode? That way, now sodium ions will be stored in this electrode and chloride ions will be stored in this electrode, okay? And then if these electrodes are saturated, then in doing so, by the way, you just remove salt and you desalinated water. And then after this, you're going to remove this electrode and then immerse the new cell. And then now you're spitting sodium and chloride out. So this is, again, reverse reaction of the forward reaction. So if this is thermodynamically downhill, it has to be uphill. So when you go through it, basically, it's like battery operation, charging and discharging. But it's just that this time, while you're using this battery through discharging and charging, you end up removing sodium chloride, and then also you get to store sodium chloride back. The question is, how can we do this? As I mentioned, there are so many researchers who are working on sodium-ion batteries. There are a lot of sodium storage electrodes. For that part, we don't need to worry about it. You can just pick and choose, okay? But what about chloride storage electrode? Okay? You have to think about, we are going to immerse this electrode in the seawater, lots of chloride, okay? So it's very, very corrosive. And then you're going to electrochemically store chloride and release, not just once. Probably you want to do this, I don't know, 7,000 times, right? So what kind of a metal? Typically, when you make metal chloride, they're going to dissolve, okay? What kind of a metal can electrochemically store and release chloride in a robust manner, okay? And then can we do that without avoiding water oxidation and reduction, right? So the key is to find robust and inexpensive chloride storage electrode. And before our work, actually, I didn't know this work, but while we are publishing our work, we are going through all the literature, and we found that there's one group who used the term something similar to desalination battery. And then that group, they used the silver as the chloride storage electrode. And then whenever you want to use this chloride storage electrode, you have to think about thermodynamics. And at the same time, you have to think about kinetics. It has to be kinetically very, very fast. If you look at this reaction, you have to realize that this is the reaction that you use for silver-silver chloride reference electrode, right? And then the key for any reaction that can be used as a reference electrode, the kinetics has to be very, very good. So kinetic-wise, this is a good reaction. The problem is, for a reference electrode, you need a tiny bit of silver so you can handle it. But if you want to build a municipal level desalination plant, silver probably cannot do that, right? So what kind of a cheaper alternative can we find to make this type of electrode? So we went through all the periodic table, okay? and then every single possible metal. And then do you know what we did? Have you guys heard about something called the Pourbaix diagram? This is for any metal. It's showing all the thermodynamically stable species. The x-axis is the pH, y-axis is the potential, and you get to see what kind of phases can form. So this is the typical Pourbaix diagram of bismuth in pure water. And then we intentionally built Pourbaix diagram in 0.6 molar chloride, okay? Because that's the concentration of chloride. And see, before here, you have a bismuth, and in a higher pH, if you oxidize bismuth, it's going to become bismuth oxide. In a lower pH, if you oxidize bismuth, you're going to make a soluble species. But if you introduce chloride, 0.6 molar chloride, now you create this gigantic island that is a bismuth oxychloride. So this becomes a new thermodynamic stable phase. And the nice news is this phase is stable between pH 0 and 10.5, and then also for a broad range of a potential. So we built this Pourbaix diagram for every possible metal in the periodic table, and we found that silver and bismuth are the only two metals that can do this. All others will dissolve, okay? So after we find this, we wrote a patent. And then here I am showing that bismuth is becoming not bismuth trichloride. It would be nicer if we can do that because we can store more chloride per bismuth. The problem is bismuth chloride is soluble. Okay? So bismuth oxychloride, and then this one has a three-dimensional structure, and this has a two-dimensional structure. And then if I'm showing the price comparison, bismuth is much cheaper. So this is as good as it gets for a chloride storage electrode. And the nice thing about this bismuth is people have to wonder, well, if you are storing chloride through an entire phase transformation, what if you form bismuth oxychloride only at the surface and it's going to passivate the surface, meaning you cannot really do the bulk conversion. The nice thing about this system is bismuth oxychloride has a two-dimensional structure. So once chloride goes in and then convert the top part of the bismuth with the bismuth oxychloride, it actually opens up like a zipper. So bismuth can keep going in and then keep transferring the underlying bulk bismuth all the way. So although this is through a through a solid state bulk transformation, because of that nice two-dimensional structure of bismuth oxychloride, you actually have no problem converting the entire bulk bismuth to bismuth oxychloride. So our first paper that was published in JACS in 2017, we used the electrodeposited nanocrystalline bismuth foam electrode. Here we deposit bismuth, electrodeposit bismuth, while we are simultaneously inducing water reduction. That way, hydrogen bubbles act as a template and you end up depositing this bismuth foam. In the beginning, we thought, making a nanocrystalline high surface area bismuth is going to help because this is through a solid state ion diffusion. So if you increase the surface area, it's going to be only beneficial. So we used this electrode to test out the property. So first, now we are going to scan the potential to the anodic way. We are going to oxidize it, okay? So bismuth, we are oxidizing it, and then you see this huge peak, and this peak is showing bismuth to bismuth oxychloride conversion. And the nice thing is once you convert bismuth to bismuth oxychloride is completely inert for water oxidation. So here you never see any water oxidation peak. And this is a good thing because when you oxidize bismuth oxychloride is the only phase to form. There's no other competing reaction. That means you're going to have 100% Faraday efficiency, meaning whatever current you flow is only for chloride storage and not about water reduction. And now I'm going to, after you make bismuth oxychloride, we are going to go to the negative direction to make sure that bismuth oxychloride can really be reduced to bismuth metal. So here, this is the equilibrium potential. For the oxidation, we see the peak right away, meaning the kinetics for the oxidation of bismuth to bismuth oxychloride is quite good. But for the reduction, the kinetic was not as good, but it's okay. Still, we are able to convert bismuth oxychloride back to bismuth. And then this is water reduction, meaning we can reduce bismuth oxychloride back to bismuth before water reduction happens. Again, this is a good news because whatever current we flow, we will be able to use to remove chloride from the electrode. We are never going to use any current for water oxidation and water reduction. And then we wanted to improve the kinetics here, and then we did the study, and it turned out if we use a 0.6 molar NaCl, that's when the kinetics is a little bit slow. But if we use an acidic solution, that acidity helps the kinetics significantly, so the overpotential decreases. The nice thing about desalination battery is chloride removal step and release step are completely decoupled. So it's not like you have to use the same electrolyte. So for the recovery step, you can lower the, let's say you can use acidify the wastewater, because there are lots of wastewater that generate acidic wastewater. If you use that, you are going to help the kinetics, meaning the potential input that's required for the reduction of bismuth oxychloride back to bismuth will be significantly reduced. And also another nice thing is bismuth oxychloride that you get to form is crystalline. So even by simple X-ray diffraction, you get to see the transformation. So this is our original bismuth electrode that is coated with the blue. After the chlorination, you see this red dot, they are bismuth oxychloride. Okay? And then we are not completely converting, okay? And then just like 50%. And then we do the dechlorination, then bismuth oxychloride completely disappears. It all goes back to bismuth. So even by simple XRD, you get to see the chloride is really removed, and then it's reversible. And then they are both crystalline. And then we did the Faraday efficiency calculation. So we are now this time really checking the chloride level in solution, and then theoretical and matching perfectly. But this is expected. If you remember, for our anodic scan, water oxidation never happened. So this just means 100% of current that you passed were truly used for a chloride removal in the solution. Okay, so then now we are ready to use this bismuth as a bismuth chloride electrode. What are we going to do? What kind of a sodium storage electrode are we going to choose to make a desalination battery? We have two options. There are, as I mentioned, there are many different sodium storage electrodes. I can group them to two categories. The first one is Prussian blue analogs. Their sodiation potential is very positive. Okay? And the other one is manganese oxide and sodium titanium phosphate, and their sodiation potential is very negative. And the chlorination potential of bismuth lies just in between, okay? So if you mix this with this this group of sodium storage electrode having a very positive sodiation potential, you're going to create a type 1 desalination battery, meaning depending on the anode and cathode potential, you know which one is going to be thermodynamically downhill, which one is going to be thermodynamically uphill, right? So if you pair this with this one, when you remove salt, that's when energy is going to come out, okay? If you mix bismuth with this one, this time when you release salt, that's going to be discharging. So depending on what kind of application you are thinking, you have to think about how you want to pair it. And then our state-of-the-art desalination battery is obtained when we mix bismuth with nickel hexacyanoferrite, okay? So that's our state-of-the-art. And then here, what I want to point out is for the sodium storage electrode, we remove 1 sodium per electron. But for bismuth, since we are making bismuth oxychloride instead of a bismuth trichloride, we spend 3 electrons and remove only 1 chloride. So it's a 3-to-1 ratio. So by the time we remove all the sodium from the seawater, we get to remove only 1/3 of the chloride. But that's okay, because in seawater, we have more ions than sodium and chloride. So our desalination battery will never produce fresh water. It's just that our desalination battery can be used to convert seawater to the brackish water, because that's the most energy intensive part. And then the remaining thing can be now coupled with RO and then ED and then capacitive deionization, because those are the ones that can do very well in a brackish water desalination. So that would be our focus. So then for our first JAX paper, we used the electrodeposited electrode. The question is, okay, can you just write a paper, or can you actually commercialize this? In order to commercialize this, we are able to write a JAX paper when our electrode is just, this thumbnail size, and then the cyclability is 200 cycles, but there is no way that you can make a company based on that. So after our first paper, we spent several years to really scale up our electrode. So this is our electrode. This is a sheet type electrode, and it's made by mixing bismuth nanoparticles and then binder and then conducting agent, and then we are roll pressing it. So this is basically the know-how of our startup company. And if I show you this without telling you that this is bismuth, you may not believe that this is bismuth metal because it looks completely like a rubber with a very good high flexibility. And then the cyclability here with a chloride storage electrode, we stopped here at 5,000 cycles, but our bismuth can now cycle to 7,000 times, meaning if we just use this as a desalination battery, it can last 5 years minimum. And then our sheet type electrode development, we can use the same method to also process sodium storage electrode, and then we can make sodium storage electrode with this type of a nice sheet type electrode. And our nickel hexacyanoferrite, the cycle time can continue up to 5,000 cycles. And this is one type of a model that we are thinking when we make this type of a desalination battery. And then if you wonder energy recovery, because this is a battery, there's a charging and discharging, what kind of energy can you recover? So I am showing here our best case scenario, meaning, as I said, at least the desalination and salination part can be completely decoupled, meaning for the salination part, you can choose the acidic medium, then you can decrease the overpotential, and that's how you're going to get a very high energy recovery, and then we can go up to 80%. But depending on the situation, if acidity is not allowed, the recovery is going to go down. But at least if we optimize the electrolyte the way we want, we can achieve a very high energy recovery. So just to summarize the advantages here, ion removal paired with energy storage, and then store energy during charging. What do I mean by this? Charging process is thermodynamically uphill, so you can see that as an energy consumption part. But if you want to store renewable energy, that charging process can actually be considered as an energy storage part, and then it can be released as a discharging process when you do the desalination. And then decouple the desalination and salination step. And then here I am saying better brine management. And what do I mean by that? Here, so this time, this is the salination, desalination. And here we have only sodium and chloride. So when we release it, we end up getting a pure NaCl. Then we can use that brine for, if we are doing this for a food processing company and they need salt, they can actually use it because this contains only NaCl and not all the reject that is obtained from the seawater. So the fact that unlike RO and electrodialysis, where desalination and salination steps are coupled, here this decoupling gives us a lot of freedom to process and then design the cells to maximize the efficiency and efficacy of the cell. And then for the salination part, it's a chloride and sodium specific. We don't need a membrane. Now, so then people have to wonder, okay, if you have a desalination, can you use this as an energy storage system? The problem is our chlorination potential of bismuth is sitting just in the middle. So the potential output here is something like 0.6 volt and 0.6 volt. So voltage wise, it's not great, okay? Although we can store and then release energy. So what we came up with is this. What if we actually utilize 3 electrodes, meaning I'm going to couple bismuth and nickel hexacyanoferrite for one step, and then bismuth and sodium titanium phosphate for one step. So here, look at this. For bismuth is storing chloride, then nickel titanium phosphate is going to store sodium. When this bismuth is going to release chloride, instead of pairing this with this, now I'm going to pair this with a nickel hexacyanoferrite. So after this, you end up with a desodiated nickel hexacyanoferrite and sodiated sodium titanium phosphate. And then you can do the discharging. So meaning 2-step charging with a smaller potential. But for the discharging part, we can add that up so that you can achieve 1.2 volt output. So that way you have the energy storage system. And then in the meantime, you also get to achieve desalination. So this is what I mean. Okay, for the charging 1 step, now you are removing sodium chloride and then you pair this way. And then now the chloride is released from bismuth oxychloride, but that time you are using a different sodium storage electrode. And then you end up with a sodiated sodium titanium phosphate, and then desodiated nickel cyanoferrite, and sodium going from here to here, you end up achieving 1.2 volt. So basically, again, because of the decoupling of the removal and then release process, you have the freedom to manipulate the electrode to achieve and add more functions. And here I am just showing the stability here, the bismuth electrode up to 7,000 cycles. They are all achieved by our sheet type fabrication technology. And then sodium titanium phosphate up to 1,000, and then nickel cyanoferrite up to 5,000. And then from these two charging process, if you think about energy input for these two processes and then energy output here, again, since we have the freedom for choosing electrolyte for a different cell, we could achieve up to 94% energy recovery, at least for the initial step. And then going back to now chloride removal, so for the wastewater, if their chloride level is a little bit higher than EPA level, all they want in wastewater facilities never to produce fresh water. All they want is just to lower a chloride level just below the EPA limit. But if you try to use RO, there's no way that you can afford the cost, right? So this basically, this is the wastewater, picture from our wastewater facility in Madison, Wisconsin. And they said every day they have to deal with 70 tons of salt, okay? And they don't know what to do. And they contacted me if we can do something with a bismuth electrode because it can remove chloride specifically. And then also we did the customer service. Okay, so we started a startup company 2 years ago. And then before we start a company, we had to go through a customer discovery because you need to understand the real customers. So our student and then the co-founders, they went through 300 total customer discovery interviews. And there are many programs in USA that support this type of a customer discovery interview because, you know, a lot of technologies fail, not because technology doesn't work out, but because professors are oblivious and they think their technology is the best, but when they actually talk to the customers, no one wants their technology. So understanding the customer's need are very, very important. So there are specific programs, and we went through interviews with a desalination plant and food processing facilities and wastewater treatment plants, and then farmers in California and Colorado, and then EPA, engineering firms, all kind of different sects. And then through our customer discovery interview, we also learned that the salt in irrigation water is a serious problem. I mean, there's a severe drought in California, then the water gets saltier, and then there are lots of vegetables and you know, things that are chloride sensitive. So then if the chloride level goes up a little bit, then the crop yield is going to decrease significantly. Again, for this irrigation water treatment, all you want is just lowering a chloride level a little bit so that it doesn't affect the crop yield. So RO or other things cannot do this. So we are hoping that our technology can do something to help the farmers and wastewater treatment. And then basically in this case, if your goal is not the desalination, but just to remove a chloride a little bit, so then here, you are going to couple bismuth electrode with the O2 reduction. So then you generate water, and then after you saturate this bismuth with the bismuth oxychloride, when you release chloride, not just removal, you can actually upgrade this chloride to chlorine gas or hypochlorous acid that is serving as a disinfectant. So you can use that in food industry or wastewater facility right away. So not just the removing it, but upgrading it to the chemicals that they want at the plant. So I'm going to tell you just a few minutes about phosphorus recovery, because we heard this morning from the first speaker about phosphorus recovery and then phosphorus. When I went through this customer discovery interview and I'm talking about chloride removal, they always ask me, do you have something for phosphate removal? Because phosphate removal is a more serious issue than chloride removal. So we also spent some time to think about what we can do. And I don't know whether you know this, there are 3 key elements for fertilizers: potassium, nitrogen, and phosphorus. And potassium and nitrogen, they are abundant. Phosphorus, the amount that, staying as a phosphate rock is limited. So according to various articles, phosphorus is considered the bottleneck of life, meaning recovering phosphorus is even more important because the amount that we have on Earth is limited. Okay, so now in the morning, we heard about the wastewater treatment part, but I'm going to show you the entire process, and you're going to realize what kind of environmental damages we are making for this entire process. We start with the strip mining of a phosphate rock, and phosphate rock is just a calcium phosphate. In doing so, basically, you kill, you destroy a lot of environment, okay? And after you make you mine phosphate rock, you want to convert calcium phosphate to phosphoric acid. That's the first thing that you're going to do. And then do you know what you do? You are going to dissolve calcium phosphate in sulfuric acid. If you know, sulfuric acid is the highest demand commodity. And guess what? More than 50% of the sulfuric acid is all used just to dissolve phosphate rock to phosphoric acid, okay? When you do that, now you have a phosphoric acid, and this leftover part, calcium and sulfate, it precipitates as a calcium sulfate, and this is called phosphogypsum. And then the original phosphate rock contains uranium and radium, so they co-precipitate. So whenever you produce 1 ton of a phosphoric acid, you end up generating 5 tons of a phosphogypsum, and they are radioactive. Think about how many phosphoric acid we have made so far, and every time we are covering the earth with a radioactive phosphogypsum all over the world, okay? So after that, we make phosphoric acid, and then you make a fertilizer, and then you eat, and then runoff, and then human consumption, and then you go, and then eutrophication, okay? So it's very important that we do something to recover phosphate. And it turned out, even for this manufacturing side, there are lots of wasted phosphate, okay? So here you generate it, and then you're making phosphogypsum, and the processed water is dumped here, and then it's cooled, and then water is reused. While you're doing this process, in this processed water and then pond water, there's unused phosphate. So we thought if we can come up with an electrochemical way to recover phosphate, and what if not just remove phosphate, what if we recover it as a phosphoric acid? If we can recover it as a phosphoric acid, we can minimize all this process, meaning less phosphogypsum and then less mining. The question is, can we do that? So the technology that we developed is again based on bismuth electrode. Here, what you're doing is you oxidize bismuth, and then if your solution contains phosphate ion, you end up making bismuth phosphate, okay? And then if you convert bismuth to bismuth phosphate, you move this, now you remove phosphate, you remove this electrode to a phosphate recovery cell, and here you are going to reduce bismuth phosphate back to bismuth. And at the same time, your counter electrode is going to do water oxidation. In doing so, protons are produced as a byproduct, and these protons and phosphate meet, and then you end up making phosphoric acid. So this is a technology where you not only remove phosphate, you can actually recover as a phosphoric acid, and that's the most versatile form of a phosphate chemical that can be used for any type of industry. Again, nicely, this bismuth phosphate, before bismuth oxychloride has a layered structure. This time it has a porous structure. So phosphorus can tunnel through this and then can go to the bulk of the bismuth, and that's why you can do the bulk conversion. I think I used all of my time, but again, everything is crystalline, so you get to see it. And then again, we did a Fourier diagram, and you get to see. The unique thing about bismuth is bismuth phosphate is stable at pH 0. That's why we can use this to produce phosphoric acid. All other metals cannot, like other metals like the aluminum and all that, they're going to dissolve in strong acidic solution. That's why they cannot serve as an electrode to produce phosphoric acid. Okay, and then I'm going to skip this. And actually the first speaker showed a similar slide here. This is the phosphate mining. Morocco has more than 70%. And as soon as we published our paper, we got an email from the company from Morocco, and then people who are developing technology, and they showed a strong interest in commercializing this entire process. So our group is going through a various de-risking process, and everything works out. Probably we are going to start a company next year for phosphate recovery. So this is my summary slide. We started in 2015. First paper, electrodeposit business, and we made a sheet type electrode, and we are scaling up. And then here, all kinds of cell. And then I just showed you our most recent work for the phosphate recovery. And here's my group. And then Do-Han Nam is our research staff who is leading our desalination effort. And then these are the all kinds of support we got for customer discovery, and then the initial concept and cyclability increase and scaling up of the electrode and all kinds of things. Thank you very much.
Well, thank you very much for a very nice and very interesting and clearly presented presentation. You indeed used all of your time, even more than that. But there are certainly quite a few questions, I think, in the audience and also in the chat. I have myself. So we will not be able to deal with all the questions, but I would like to give at least a couple of minutes at a time for answering questions.
Thank you for your great talk. I have a question about the release from the bismuth oxychloride and then releasing the chloride. So your bismuth chloride is 2D, and then when you release the chloride, it becomes 3D. And 2D has a channel, but then 3D doesn't have channel. So what's the regeneration percentage?
The directions are different. When it's going in, it's from bismuth oxychloride to bismuth. When it comes out, bismuth to bismuth oxychloride. So it's now jipping, unjipping and jipping.
So is it going from, when you go from the bismuth oxychloride to bismuth, is it starting from the
solution to electrode? And for the back reaction,
electrode to solution. So is the regeneration 100%, close to 100%?
Yes, 100%.
A question over there. You.
Thank you, Professor, for your wonderful presentation. I have a question according to the chemical reaction formula, because according to the chemical reaction formula, when the electron capture the chloride, some hydrogen ion will be released. So would the pH value change if the problem during the desalination process?
Yes, yes. So what she's asking is, since I am converting to bismuth oxychloride, oxygen is coming from water, meaning proton is generated as a side product. So then while we are removing chloride, then because of proton, the pH is going to go out. Yes, that actually happens. So if you do it in the seawater, because of the CO2 that's dissolved, there's some sort of a carbonate buffer. So you end up removing CO2, so the pH drop is not going to be significant. So depending on what kind of water that you are dealing with, no matter what, pH is going to go down. But if there's a carbonate buffer, you actually end up removing the carbonate buffer, so pH is not going down. But as you heard from the previous talks, if you have an acidified desalinated water, that's not necessarily a bad thing, because that can prevent scaling for the next step. So depending on where it's going to be used, we can actually be clever to utilize the protons that are generated from the process.
Thank you. Thank you for your
question over there.
Okay, thank you very much. My question is about your bipolar design for the charge-discharge case. Because you say that when you're doing acidic solution, when you try to reduce the BiOCl, the overpotential become reduced. But in this case, I mean the bipolar design, how can you overcome the overpotential issue?
What do you mean by bipolar design?
Because you're using the
three electrode?
Yes, one is bismuth, and then
yes.
Right.
So this one here, 0.6 molar NaCl. This one we used low pH to lower the overpotential.
Right, but you're doing charge and discharge. So only doing charge, because for this case, I mean the chlorination is acidic solution favorable, and this one is neutral favorable. So This because
the
in
number
your
is not
case,
coming
I think you also
very
doing the
faster.
charge and discharge for the bismuth electrode
Huh?
because it's beside these two electrodes. Is that right?
Need
Or I got the wrong understanding.
So this is basically, if you think about it, every cell has 2 electrodes.
Right.
Overall, I have a 3 electrodes. So here you need to have a very unique design of the cell. So 3 electrode position.
So this is done a bipolar design.
I
Okay,
don't
because in
understand-
electrochemistry,
I don't understand what you mean by bipolar.
bipolar that indicates, okay, this one, for your case, bismuth can work as an anode and also cathode simultaneously. Okay, so for this one, when we're doing charge, this is oxidation and bismuth may be reduction, but another side is
Right,
oxidation
right.
and then
Right.
reduction.
Right.
So this is, I say, the bipolar.
Yes.
So your case is not bipolar design.
There are multiple ways to design this cell. I can give you one example. Imagine that there's a one tank and 3 electrodes are all in there, but there can be like a compartment. And then that compartment slide in and sliding out is changing. So with 3, this can be 2, and then you inject water. And then after that, now this compartment, and then you inject another water and it goes out. So every time there's a cell, there will be only 2 electrodes, bipolar, but the design is not conventional, the portable type one with just a fixed 2 electrodes.
Okay, thank you.
Okay, there are also questions online, and it would be unfair not to also look at those questions. So there are actually quite a few online. We cannot handle all of them, but I cannot see them. Oh, here they are. You can choose the question you like.
Okay, so I'm going to choose the second one. Okay,
From
how
Subway
the
Sun. Okay, yeah.
how the salt concentration affect the kinetics of dechlorination. Of course, everything is going to follow the Nernst equation. So if you have a more dilute chloride, you have a less overpotential. More chloride, it's going to have a difficult time. I mean, it's going to require more energy. So the best state, the energy efficiency that I showed you is just the earlier stage. And if we do the complete desalination, energy recovery is going to go down. And then it's the sheet electrode pure bismuth. It contains the electrochemically active material plus binder plus conducting agent.
Okay. And I actually also had a question about the introduction of the chloride. What is there the rate limiting step if the chloride is entering the bismuth structure? Is that the opening? Yeah, the rate limiting step. Is that the diffusion in, or that the opening of the structure?
I actually do not have a way to deconvolute those steps because going in opens up, right?
Yeah.
So at this point, I don't have a a way to tell exactly what is fundamentally limiting.
But it's rather quick, as you showed.
Yes.
Is it? Maybe you can answer also the last question on the fabrication, the electrode fabrication.
This one actually, our initial JAX paper is showing all the details. So I tell this person our 2017 JAX paper, it's actually very easy to make it.
Yes.
So I think first year graduate student can make it. So please look up the paper.
Okay. Okay, well, thank you once again. I also noticed that this is actually a presentation really fits into the title, the new title, battery deionization. So that's also very nice to
thank you
to see. Then I will now hand over to the organizer. We're a little bit running over time, but I think you can handle that.
Okay, now we will break for lunch until 1:30. Lunch can be enjoyed in the lobby as well as in room 205 and 2304. Please remember that food and beverage are not allowed inside the conference hall. Thank you for your cooperation. And for poster and oral presenter, if you haven't set up your poster or present slides, please kindly do so during the break time.